In this video, I want to talk about a second way that the chi-square test can be used, namely to test for the independence of two attributes. This table that you see on the screen is the Mendel's plant experiments again. These are the same 9 numbers that we saw in the other video, except I've divided them by the genotype for color and the genotype for roundness. So there were 38 pea plants which were dominant homozygous for both color and for roundness, and there were 138 that were heterozygous for both attributes, and so on. So the question is, are these two attributes independently inherited, or are they somehow dependent? Mendel's laws postulates that these attributes are independently inherited, and the chi-square test can be used to test for the independence of two attributes. The way that we do this is, here is our observed data, and we assume the null hypothesis that the two attributes are independent. The alternative hypothesis is very modest and simply says that the two attributes are dependent. Next, we have to figure out the number of expected things. So there's the observed, and down here, let me start making another table to show the number of expecteds that we would have. The way that we compute the number of expecteds under the null hypothesis is that we first have to compute the row sums and the column sums. So I need to add these three numbers up to get 126, and filling down I get 132. Also, I need the column sum of 38, 65, and 35, which works out to be 138, and filling across we have 265 and 126. And the sum of the sums, the sum of all 9 numbers, is 529. So there are 529 total things here. And let me put this in a shade so we can say so those are the actual numbers, and these are just the sums that we see. Under the null hypothesis, the chance of being in this block here, so the chance of being in that block is, well, there's 126 chances out of 529 of being in that row, and 138 chances in 529 of being in that column. So if the attributes are indeed independently inherited, then the chance of being in the upper left-hand corner of the table would be equal to 126 over 529 times 138 over 529. So therefore, the number of things in here would be the chance, which is 126 over 529, times 138 over 529, times the number of things in the list, which is 529. So 126 over 529 times 138 over 529, that product is the chance, and I multiply by the number of experiments, and that would be the expected number of things in that block. Clearly, 529 cancels one of the 529s on the bottom, and so this can be more succinctly written as 126 times 138 divided by 529. So that would be the number of expected things in the upper left-hand corner of the table, if indeed the null hypothesis is correct. Likewise, this number would be equal to 126 times 265 over 529, taking this row sum times this column sum over the total sum. So I would expect 63.11 things in that block. Now, if I have a calculator, I just simply repeat this calculation 9 times until I figure out all the expected values. Using Excel, there's a little trick that we can use to do this. The trick is to take this number times this number divided by this number. Okay, now I have to be careful about how I fill things down. So in here, I need to have dollar signs around the e's to make sure the 529 does not move when I fill. Around this one, I need to have a dollar sign on the left, and on this one, dollar sign on the right. Now, I'll be perfectly honest, I can never remember which way this goes, so if I fill down and it doesn't work, then I'll swap the dollar signs on the first two terms. So let me fill and see if it works, and it looks like it does work. Okay, so the double dollar sign means that the 529 never moves. The single dollar sign on the left here means that when I fill across, the 138 will move, but the 126 does not. So if I highlight this cell here, the 126 stayed put, but the 265 changed. And of course, the 529 did not change. Going downward, if I look at this cell, 279 moved down a row, but the 138 stayed in the same column. And so I get a correct reference when I look at that cell. So those are my 9 expecteds. Next, I figure out what this chi-squared statistic is. To get the chi-squared statistic, I proceed as before. It's going to be the observed minus the expected that goes with it, squared divided by the expected. A technical point, we want to make sure that all of the expecteds are at least equal to 5 for this little trick to work. So there's my observed, there's the term for that one upper left-hand corner. Then I repeat this for the other 9, or all 9 entries in the square, so that this last term here is going to be 30 minus 31.4405 squared, all divided by 31.4405. And finally, the chi-squared statistic will be equal to the sum of these 9 numbers, which is 1.857. So there's the chi-square statistic. I don't need this little side calculation anymore. There's my test statistic for my chi-squared. Now, what does this test statistic mean? In this, when I have a contingency table like this, the number of degrees of freedom will be the number of rows minus 1 times the number of columns minus 1. So 3 minus 1, 2 times 3 minus 1 for 2, 2 times 2, I have 4 degrees of freedom. So for a contingency table, I have a slightly different way of calculating the number of degrees of freedom than I had when I was testing proportions. So I have a chi-squared distribution with 4 degrees of freedom, and I have a chi-square statistic of 1.857. So the picture kind of looks like this. Here's the, whoops, sorry about that. I have the coordinate axes. The chi-square distribution kind of goes like this. 1.857 is going to be over here someplace. Why do I know it's over here? Turns out the chi-square distribution for 4 degrees of freedom has a mean of 4, so it gives me kind of an idea as to where that number should be. So there's my observed test statistic, 1.857. And the question is that enough evidence to retain or reject the null hypothesis? Now, just like before, we have 2 ways of making this determination. The first way of making the determination is to figure out the area to the right. To find the area to the right, the p-value, I use the command chi-squared dist RT. So that's the area to the right under a chi-square distribution, starting at this point with 4 degrees of freedom. And that works out to be about 0.76202. That number is larger than my alpha. Alpha is not prescribed in the problem, so our default value is 5%. And so my conclusion will be to retain the null hypothesis. So that's one way to go about the problem. The second way of going about the problem is to figure out the critical value. The way that we find the critical value is, instead of comparing areas, we compare x-coordinates. So the critical value is, I want to figure out the number here, critical value, so chi-squared sub c critical, so that the area to the right of this mark is exactly the value of alpha, which in our problem is 0.05. Now I can do this in Excel by using the command chi-square inverse.rt. That returns the inverse, the critical value, if I have a probability of 0.5 and 4 degrees of freedom. That cutoff value is 9.488 approximately. So this number here is about 9.488. Okay, and therefore, if I have a value over here, the area to the right has got to be bigger than 5%. So if I have any x-coordinate that's over here, my decision will be to retain the null hypothesis. However, if the critical value turns out to be to the right of this line, the decision will be to reject the null hypothesis. So I can make the determination about whether to retain or reject the null hypothesis two ways. I can compare areas directly, which means comparing p to alpha, or I can compare x coordinates directly, comparing my test statistic to this critical value. Both methods are logically equivalent. Excel permits us to do it both ways. As shown on the other video, the TI calculator, at least the TI-83 Plus, will permit calculation of the p-value. To my knowledge, it is not possible to calculate the critical value on a TI-83 Plus, though it may be possible on other graphing calculators. Also, if you're unable to do this with the graphing calculator, there are tables in the back of the book that will give that particular critical value. So the tables in the back of the book will give the critical value as opposed to the p-value. So the TI-83 can compute the p-value, and the table in the back of the book will compute the critical value. Excel will do both. So in conclusion, we retain the null hypothesis, H0. And we conclude that it appears that the attributes are independently inherited, which is one of Mendel's laws of genetics, that the attributes of different characteristics are indeed independently inherited, that the P shape and the P color are, whatever happens in the next generation, do not affect each other. So, in conclusion, there are two applications of the chi-square test. We can use the chi-square test to test a list of proportions that are assumed. That was described in the other video. Also, in this video, we've seen how the chi-square test can be used to test for the independence of two different attributes.